The Big Bang marks the starting point of the universe's evolution from an initial state of extreme density and temperature, conditions so intense that we currently lack the technological means to replicate them. Because these earliest moments and environments remain beyond our experimental reach, any explanation of what triggered the Big Bang itself must be approached with a healthy dose of skepticism. Still, it is only natural to wonder, what existed before the Big Bang? One answer may be that the very question doesn't carry the meaning we assume. While we can parse the sentence, "What was there before the Big Bang?" in everyday language, it may be that, in a cosmological context, this question is simply nonsensical. One reason is that the Big Bang could mark the origin of time itself. We can sensibly talk about events a few billion years ago, even 13 billion years ago, but going back 13.8 billion years brings us to a boundary where time may have begun. If time started at the Big Bang, then there was no before for anything to inhabit. Our current understanding of how the universe evolved comes from a careful blend of theoretical models and astronomical observations. The Big Bang theory, built on the foundation of Einstein's general relativity and supported by a wealth of data, describes how the cosmos expanded and cooled from an ultra-dense, scorching hot beginning. Yet, the theory does not explain what caused the Big Bang or how space, time, and energy were initially created. Rather, it describes how our familiar universe emerged from an initial, incomprehensibly extreme state. At the heart of this mystery lies the need for a complete theory of quantum gravity, one that successfully merges the principles of general relativity with quantum mechanics. Today's known physics break down at the Planck epoch, the earliest known era of the universe. Without a robust quantum gravity framework, we are left with speculation. Some approaches in quantum gravity suggest that time itself might be an emergent property, meaning that time may not have existed before the Big Bang. Others remain open to the possibility that something else existed prior to that moment, but we currently lack the data to say for sure. In truth, there is nothing problematic with allowing negative time, if a future theory demands it. Our choice of when to set the cosmic clock to zero is arbitrary. If new discoveries push our understanding beyond the Big Bang, we might simply redefine the 0 point or measure time into negative values. Timekeeping is, after all, a human construction. One appealing idea among physicists is that gravity can appear in two forms: the familiar, attractive kind we experience daily due to massive bodies like Earth and the Sun, and a repulsive form that arises when energy is uniformly distributed across a region of space. In certain early universe scenarios, this repulsive gravity, associated with something like an inflaton field, could have driven the initial rapid expansion, this bang from which everything emerged. Thus, the Big Bang might have been sparked by a tiny region of space infused with repulsive gravity, propelling it outward. It is important to clarify what the Big Bang theory does and does not do. It does not claim to describe the ultimate origin of energy, space, and time. Instead, it explains how our current observable universe evolved from a hot, dense initial state. When cosmologists say the universe was once the size of a grapefruit, for instance, they are referring specifically to the observable portion of the universe at that time, not necessarily the entire cosmos. To better understand the universe's earliest phases and subsequent evolution, cosmologists map out a chronology of cosmic history. According to the Big Bang model, the first tiny fraction of a second, around the Planck time, remains a realm where known physics breaks down. Soon after, the fundamental forces emerged in stages: gravity first, then the strong, weak, and electromagnetic interactions. The universe underwent a period of cosmic inflation, stretching minuscule quantum fluctuations into the seeds of future galaxies. If we could look at the universe just 1 second after the Big Bang, we would see a 10 billion degree sea of particles: neutrons, protons, electrons, positrons, photons, and neutrinos. As time passed, minutes, hours, millennia, these particles cooled and combined, leading eventually to stable nuclei and, much later, neutral atoms. By around 370,000 years, electrons had joined with nuclei, allowing photons to travel freely for the first time, filling space with a faint glow known today as the cosmic microwave background, CMB. The CMB stands as our earliest snapshot of the universe. Yet, we still know very little about what, if anything, came before that hot, dense phase. Many hypotheses attempt to push beyond the Big Bang. Some imagine that the Big Bang was merely one event in a grander cosmic landscape, perhaps preceded by other Big Bangs, or by a multiverse teeming with bubble universes. Other theoretical frameworks, from the Hartley-Hawking no-boundary proposal to various string-inspired scenarios like the pre-Big Bang and ekpyrotic models, suggest that what we call the Big Bang might not have been a singular starting point at all. In eternal inflation models, for example, our Big Bang might be just one local bubble nucleation in a vast multiverse, with other bubbles popping into being elsewhere, each with its own Big Bang. Alternatively, cyclic models envision a universe that repeatedly undergoes expansions and contractions, so that one universe's big crunch is followed by another's big bang, creating a never-ending cosmic cycle. Without a complete theory of quantum gravity or observational evidence for conditions before the Big Bang, we may never fully understand the universe's ultimate origins. It might turn out that the question, what happened before the Big Bang, is fundamentally unanswerable, or even meaningless. But that will not deter scientists. Humanity's strength lies in its curiosity and its determination to push knowledge as far as it can go. As research continues, powerful telescopes, gravitational wave detectors, particle accelerators, and ingenious theoretical advances may help us glean new insights into the mysteries of cosmic birth. Whether we discover that time itself began with the Big Bang, or that ours is one of countless universes in an eternal cosmic panorama, we will continue to ask the big questions, driven by the spirit of inquiry that defines both science and civilization. Thank you for watching. If you enjoyed this exploration, please consider subscribing and enabling notifications to never miss future videos on these and other cosmic mysteries.